computer. Okay, so yeah, so today we have Rajas from IIT Pune. So he basically completed his PhD from ISC with Professor Vamsi and Professor Ved, and he's working currently as a postdoctoral fellow at IIT Pune. So he works in Kähler geometry, and today he will be talking on the existence of higher extremal Kähler metrics on a minimal ruled surfaces, and that is the first talk where he will be talking some prerequisite about the Kähler manifolds. So yeah, Rajas, you take over.
Okay. So thank you, Sachidanand, for introducing me, and thanks to all the organizers for inviting me for this seminar series. So I will immediately begin my talk. In this series of talks, so I will be having 3 talks in this series. So they will be about this existence of higher extremal Kähler metrics on a minimal ruled surface, which is my first published research paper. So the central objects in this research paper are what are called as these higher extremal Kähler metrics. So in Kähler geometry, in the study of these what are called as canonical Kähler metrics, so there are some metrics in Kähler geometry which satisfy some nice curvature properties, and such metrics are called as canonical Kähler metrics. The most basic examples of these are Kähler-Einstein metrics, which are simply Kähler metrics such that the metric tensor is directly proportional to the such that the Ricci tensor is directly proportional to the metric tensor. Those are Kähler-Einstein metrics. And then there are
So
Kähler
Rajas,
metrics of
are you also changing the screen, or it's on the first slide only yet?
yeah, I will change the screen. I will do that.
Okay, no, I thought you were changing, but it was not changing. Okay, that's fine. Okay.
Yeah, I was just giving us a brief review. I will share change the slides as well.
Okay, okay.
So then the main idea in this series of talks is to discuss about these canonical Kähler metrics, which are some Kähler metrics which satisfy certain nice curvature related properties. So let me first tell what is the background material that I'm assuming. So first of all, I'm assuming that the audience knows is familiar with differential geometry, which is the theory of smooth manifolds. And all the things in the theory of smooth manifolds people are familiar with. That's what I'm assuming. Then in Riemannian geometry, we don't need any higher level things, but at least the definition of a Riemannian metric on a smooth manifold, and then this Levi-Civita connection, and the notion of curvature, which is induced by the connection. So these are the things. And then apart from that, one variable complex analysis, of course, is assumed, and in this several complex variables. So because I'm going to be talking about complex manifolds, complex manifolds are basically manifolds whose charts are lying in Cn. So then the theory of holomorphic functions of several complex variables comes into play. But here we are not really using any hardcore SCV. We only need some very basic facts from SCV. So this is the thing that we need. So I hope that people are also able to see the cursor, so that where I'm pointing, you all can see. Okay, so we need to know that what is a holomorphic function of several complex variables. So let us say that we have a domain capital G, which is a subset of Cn. So domain means non-empty open connected subset of Cn, the nth complex space, the complex n space. Then f from G to C is a function. So when is f said to be a holomorphic function? So then the complex variables, let us say they are Z1 up to Zn. So f is said to be holomorphic on the domain G if it is holomorphic in each variable separately, meaning we restrict for each I from 1 to n, f considered only as a function of zi, that is a holomorphic function of one complex variable, then such an f is said to be uh, holomorphic on the whole domain. So like this is actually an equivalent condition of holomorphicity of a function of several complex variables, but we can also use it as a definition. So this is our definition of a holomorphic function of several complex variables. And apart from this, of course, one thing that we need are these Dolbeau differential operators. So maybe like what I can do is in between, I can try to write on whiteboard as well and share that if that will be fine. Okay. So I will try to write what are these Dolbeau operators on a whiteboard. Can everyone see the whiteboard?
Yes,
Is
yes.
okay, sure. Yeah. So we know that this operator D, which is the exterior differential. So sorry for the bad handwriting. I'm writing using the cursor. So suppose we have this small f as a real valued function defined let us say on Rn or on some open connected subset of Rn. So then this df is the total differential of f, and that is the nothing but we take the partial derivatives of f with respect to x1 up to xn. Del f by del x1 dx1. Sorry. And then we take the sum over I. So this is what is called as the total differential of f. So then similarly in complex variables, we have del f and del bar f. So now let us say f is a function defined on some domain in Cn. So then we have one called as del f, that is nothing but the partial derivative of f with respect to z1, and then dz1. Then once again take the sum as I varies from 1 to n, and we have del bar f. So over here now we take del f by del z1 bar dz1 bar. This sum of this as sorry, the sum of this as I varies from 1 to n. So the thing is that what is this del by del zi and what is this del by del zi bar? So zi and so zi will be equal to xi plus square root of minus 1 times yi. Zi bar will be the conjugate xi minus square root of minus 1 times yi. So then these are actually, so this is for example equal to 1 by 2 times del by del xi plus square root of minus 1 times So usually, like I try to write square root of -1 instead of writing I or j, because then that gets confused with the index. So del by del zi bar is equal to half 1 upon 2 times brackets del by del xi plus square root of -1 times del by del yi, and then del by del zi will be half of del by del xi minus square root of -1 times del by del yi. So then we have these z1 up to zn and z1 bar up to zn bar as the complex coordinates, where z1 up to zn, these zi's are called as the holomorphic coordinates, and these zi bars are called as the anti-holomorphic coordinates. So now, in this, if del bar of f is 0, then so del bar of f is 0 if and only if del f by del zi bar is 0 for every I from 1 to n. This is same as saying that f is a holomorphic function. And similarly, if del f were 0, then del f by del zi would be 0 for every I, which is same as saying f is an anti-holomorphic function. So f is a holomorphic function is equivalent to saying del bar of f is 0, and f is anti-holomorphic is equivalent to saying del f is 0. And actually these del f by del zi bar, they will is equal to 0. These will indeed boil down to n Cauchy-Riemann equations. If you write down f in terms of its real and imaginary parts, say u plus square root of -1 times v, then this del f by del zi bar is equal to 0 for every I. This condition will actually boil down to the n Cauchy-Riemann equations for the variables xi and yi. So so then that's what is meant by saying that a function is holomorphic if and only if it is holomorphic in each variable separately. So we are using these del and del bar operators, which are called as Dolbeau operators. So okay, I will now once again go back to my slides. Okay. So now uh, now that we know one minute. Yeah. So now that I just discussed about some things about this holomorphicity of functions of several complex variables. So I will just start by first giving the definition of what is a complex manifold. Okay. Wait. Yeah. I hope that the screen is visible to everybody. Okay. So a complex manifold is nothing but a smooth manifold such that the charts are holomorphic. So what does that mean? So just like for a smooth manifold, we first start with a connected second countable metrizable topological space, capital M, or sometimes we take instead of metrizable, we take it as paracompact and Hausdorff, doesn't matter. And then n is a fixed non-negative integer, which is going to be the dimension of this manifold. So then we have an open covering of the manifold U alpha, and we have these homeomorphisms of these open sets U alpha going into some open subsets of Cn, where this n is fixed. So then these are homeomorphisms, and over here, these transition functions, instead of being smooth, now we want them to be holomorphic. So if this is the case that all the transition functions are holomorphic, then such an atlas is called as a compatible holomorphic atlas, and that gives a complex structure on the manifold capital M. And then capital M with this complex structure is called as a complex manifold, and the complex dimension, the dimension over C, the dimension over complex numbers of this manifold is small n. So one thing that we can quickly observe is that since these charts are going into open subsets of Cn, and Cn can be identified with R2n as a vector space over the reals. So that's why this capital M will be having an underlying smooth structure of real dimension 2n. So the real dimension will be twice of the complex dimension. Okay, so now, this is what we mean by a complex manifold. So the most important thing is that once we define a smooth manifold, we want to see can we make sense of a smooth function defined on the manifold. So over here, we want to make sense of a complex function, sorry, a holomorphic function or a complex analytic function defined on the smooth manifold. So now we know what are complex analytic or holomorphic functions of one complex variable as well as several complex variables. So now we will try to define a holomorphic function on this complex manifold. Uh, just a second. Sorry, I think I got logged off. Yeah, okay. So a holomorphic function defined on a complex manifold. So f from m to c is said to be a holomorphic function if on every chart this f composed with the inverse of that chart map is a holomorphic function. So the inverse of so f composed with the phi alpha inverse, that will be a function defined on a open subset of C and to C, and we know what it makes sense. We know what it means by a holomorphic function on a domain in Cn to C. So that's why. So this is the definition of a holomorphic function on a complex manifold. So similarly, now we have this f from M to C. We could have. We can also make sense of f from capital M into C raised to the power ck sum. So. So that will be holomorphic if and only if all the component functions are holomorphic. And then now if we have two complex manifolds, let us say capital M and capital N, so then when is the function f from capital M to capital N a holomorphic function? We will have to just compose with the chart function of capital N as well instead of C over here. So then that will be some psi composed with f composed some psi beta composed with f composed with phi alpha inverse. That should be a holomorphic function. So similarly, we can make sense of a holomorphic function between any two arbitrary complex manifolds. Okay, now I will just give some examples of complex manifolds. So, of course, the first very standard example that will come in our mind is this Cn, which of course has to be a complex manifold. So, Cn is a complex manifold of complex dimension n, and more generally, any domain in Cn will also be a complex manifold. So, this punctured complex plane and the standard unit disk. These are two very important examples of complex manifolds. And then the first non-trivial example of a complex manifold that we have is S2, the Riemann sphere, uh, which is the two-dimensional sphere over the as a smooth manifold, but that also has got a complex structure. So how it has got a complex structure is that so on S2, we know that we have this stereographic projection onto the complex plane. So we take two charts on S2. One is S2 minus the south pole. Another is one is S2 minus the north pole. Another is S2 minus the south pole. And then the charts are going to be the stereographic projections onto the complex plane. The only thing over here is that to make the transition functions holomorphic, we just need to add one more thing, that in one of the charts we will have to after taking the stereographic projection, we have to also take complex conjugation, means we have to compose it with the complex conjugation map, and then the transition function will turn out to be some function from c minus origin to c minus origin, z going to 1 upon z, which is a holomorphic function of one complex variable. So that's why this S2 is a complex manifold of dimension 1, and we call such manifolds Riemann surfaces. So S2 is an example of a Riemann surface. This standard unit disk, that is also a Riemann surface, and similarly the whole complex plane C, that is also a Riemann surface. Okay, I hope the whiteboard is now visible. So there is like I will now immediately just say about this uniformization uniformization theorem for Riemann surfaces. So like Riemann surfaces, as I told, are complex manifolds of complex dimension 1. So as real manifolds, as smooth manifolds, they will have dimension 2. So that's why we call them Riemann surfaces. So the uniformization theorem says that uh, all that any compact connected Riemann surface is up to bioholomorphism uh, any of the following model spaces. I will just draw them. So one is the complex plane C, which we of course know. Another is the sorry, okay, sorry, I said compact. Sorry, no, not the. So say that this is the Riemann sphere S2. So this is the Riemann sphere S2. So any compact Riemann surface, compact connected Riemann surface up to bioholomorphism is either the Riemann sphere S2 or it is the complex torus, which we will also see is a complex manifold. So the complex torus, or it is a connected sum of complex tori. So I will explain in the coming slides why is the complex torus also a complex manifold. And then once the complex torus is a complex manifold, we can just take the connected sum of the complex torus with itself as many times, finitely many times as we want to, and then that gives us compact complex manifolds of complex dimension 1, so compact Riemann surfaces, which have got genus 1, 2, 3, and so on. So the thing is that this sphere S2, as we will see in the next lecture, it has got uh, it has got a Riemannian metric, or in this case a Kähler metric, which will have curvature strictly positive, or we can say we can scale it so that it has got constant scalar curvature 1. So on the torus, it has got there exists a metric having curvature 0, and then these uh, connected sums of at least two tori, these have got Kähler metrics of negative scalar curvature. So these are the so the uniformization theorem thus is equivalent to the classification theorem for surfaces. So this theorem classifies what are all the compact Riemann surfaces, and another version of the uniformization theorem also says that given any simply connected Riemann surface, it has to be bioholomorphic to one of these three model spaces. So the first model space is S2, the Riemann sphere. the second model space is the complex plane, which I can draw something like this: 1 and square root of minus 1. This is the complex plane. And the third model space is the standard unit disk in the complex plane, which I denoted by the symbol D. So by the Riemann mapping theorem of one variable complex analysis, we know that any non-empty proper open subset of the complex plane, which is simply connected, it has to be biholomorphic to this disk. So that's why the complex plane theorem for Riemann surfaces says that any connected, simply connected Riemann surface is biholomorphic to one of these three model spaces. So again, over here, this Riemann sphere has got curvature 1. The complex plane is flat; its curvature is 0, and the disk is going to be having the Poincare disk. So it has got negative curvature. So it's a hyperbolic metric. So
Sorry to
the thing
interrupt.
is that yes,
Uh,
yes,
I have a question. Can I?
yes, yes, sure, sure, definitely.
You're saying they're all any space, any Riemann surface is biomorphic to one of these three.
Yes.
So if it has curvature, uh, like if it has non-constant curvature, the biomorphism will change the curvature and make it constant curvature.
So the thing that we need to note here is that first of all, curvature comes from a metric. So up
Yeah.
till now, I have discussed only these complex manifolds. So if there is no metric on the manifold, it does not make any sense to talk about curvature. So
Yeah.
that's why, so the thing is that in the next lecture, I will introduce the notion of a curvature more precisely. Yeah, so the thing is that this Riemann sphere will be having a Kähler metric or uh, which, which is basically a Riemannian metric which is compatible with the complex structure. So the Riemann sphere has got a Kähler metric of constant scalar curvature equal to 1. And the complex plane, it is having curvature 0 Kähler metric or a flat Kähler metric. And similarly, this Poincare disk, it has got constant scalar curvature -1. So yeah, so that's
Yeah,
like
so my question is that can you are you saying that you can give any Riemann surface a Kähler metric which is constant curvature, or can you make a biomorphism between any Riemann surface and a constant curvature Riemann surface? That does
yeah,
not like, that seems to me like the biomorphism thing, like any surface is biomorphic to constant curvature.
yeah. So once you give the biholomorphism, you can pull back the metric by using the biholomorphism, right?
Yeah, so but the curvature will not change, right? Under the
Mm,
biomorphism.
yes, correct. The curvature.
So if I
One
start
minute.
with something which has non-constant curvature, the biomorphism cannot make it constant curvature.
Yes, correct, correct. Yeah.
So it has to be something like a conformal change, I think, not biomorphism.
And biholomorphism will be conformal.
Yeah, no, but I think the statement can be like it is in the conformal class of some constant curvature metric.
Yeah, yeah. So like you are saying that instead of having this stronger thing of a biholomorphism, we can it will even work if we have a conformal equivalence.
Yeah, because I remember seeing the statement some time ago, and I think that was the statement, like it was conformal change and not biomorphism.
Uh, yeah, but yeah, so that is true. But since over in this series, I'm discussing about only complex manifolds. So that's why
Yeah,
I just took it to be a holomorphic thing. Anyway, a holomorphic thing is always going to be conformal.
yeah, that's
Any
true.
holomorphic function is conformal.
Yeah, right. Thank you.
Okay, yeah, yeah, sure, thanks. Yeah, so yes, so this is about the uniformization theorem for one for compact Riemann surfaces and one for simply connected Riemann surfaces. So it turns out that these the Riemann surfaces that I have shown below, they are the universal covers of the Riemann surfaces above. Okay, uh, holomorphic universal covering spaces. Okay, so okay, I will once again go back to the slides. Okay. Yeah, over here, and then we can also get these matrix groups, which will be complex Lie groups. So, like, remember that a Lie group is a real Lie group is nothing but it's a group first of all, and it has got a topology, making it a topological group, and on top of it, it has got a manifold structure such that the group operations of multiplication and inversion, they are smooth maps. So that's what is a real Lie groups. So a complex Lie group is similar. It's additionally a complex manifold such that the multiplication and inversion operations, they are holomorphic now. So these are called as complex Lie groups. And then the standard examples again come from the matrix groups. MNC is of course the set of all n cross n matrices with complex entries under addition. So this is nothing but c raised to the power c raised to the power n square, cn square. So of course this is a complex manifold, and most importantly, glnc and slnc, the general linear group over complex numbers and special linear group. So this is the set of all invertible n cross n complex matrices, or determinant non-zero n cross n complex matrices, and this is the set of all SLNC is the set of all n cross n complex matrices whose determinant is equal to 1. So it can be checked that these are complex manifolds of dimensions n square for MNC, n square for GLNC as well, because GLNC is an open subset of MNC, because the condition determinant is not equal to 0 means that it's an inverse image of singleton zero complement, and inverse image of an open set. So that's why GLNC is an open subset of MNC, so an open submanifold. So that's why its dimension will be same as n square. And then this SLNC, we can check it. It has got dimension n square minus 1. So these are again complex dimensions. Okay, and then a fact which can be seen quickly is that every complex manifold is orientable. So a quick way to see this thing is that on this complex manifold, these transition maps, phi beta composed phi alpha inverse, they are biholomorphic maps. So so an equivalent characterization of orientability is that every the Jacobian of every transition map should be strictly positive, or of every transition map should be strictly negative. That is, all the Jacobians of transition maps should have the same sign. So over here we can see that the Jacobian of this phi beta composed phi alpha inverse over the real numbers. So like when we talk about orientability, we are considering the underlying smooth structure. So so the Jacobian of this phi beta composed phi alpha inverse, but because this is a holomorphic function, so that's why the entries of the Jacobian matrix, they will be satisfying the Cauchy-Riemann equations. So then if we just take a holomorphic function of one complex variable, and we write it as f is equal to u plus square root of minus 1 times v, where u and v are the real and imaginary parts. So then the Jacobian matrix, as we know, is going to be u. Okay, so the Jacobian matrix is going to be ux u subscript x, where this is the derivative, partial derivative of u with respect to x, vx uy and vy. So, and then the Cauchy-Riemann equations say that ux is equal to vy and uy is equal to minus of vx. So then the determinant of the Jacobian matrix will be ux square plus uy square. And then these are real functions. So that's why ux square plus uy square has to be strictly positive. So that's why the Jacobian of every uh, transition map is strictly positive, and that's why the manifold has to be orientable. So this is how we see that every complex manifold is orientable. Okay, and then some more examples of complex manifolds. One, as we know, is the open complex submanifold. You take any domain in the complex manifold, that will also have will be a complex manifold of the same dimension. And now, for getting examples of this SLN of examples of the type of this SLN of C, so we use this constant rank theorem, which we have from differential geometry, that carries over to complex geometry as well. Namely, if you have a holomorphic map, either from M to C or from M to N, where M and N are any arbitrary complex manifolds, then and if this holomorphic map has got constant rank over C, and then that rank is R, so then the inverse image of any point belonging to the image set, this level set, so this level set will then be a complex manifold of dimension n minus R. And then for this SLNC, we take the determinant map, and then this is the level set of 1 under the determinant map, and that's why it has got dimension n square minus 1. So we have this constant rank theorem over here as well. So these will be, of course, closed complex submanifolds, and we get closed hypersurfaces. So their codimension is 1. So these are hypersurfaces. Okay, and then most importantly, we have these quotient spaces, and that's how we prove that the complex torus is a complex manifold, because it's a quotient space. So okay, so first is the orbit manifold of a holomorphic Lie group action. So first of all, this complex Lie group, it has to act holomorphically. That is the action function dot from G cross M to M. That should be a holomorphic map with G cross M endowed with the product manifold structure. If that is the case, and on we need two conditions for this action to satisfy. Namely, it should be free, meaning fixed point free. There should not be any fixed points, and it should be proper. So if it's a free and proper action, proper means the function from G cross M going into M, G cross M going into M cross M, G comma P, where G is a point of the group capital G and P is a point of the manifold capital M, G comma P mapping to G dot P comma P. This should be a proper map, meaning inverse image of compact sets should be compact. So if the action is free and proper, then this M mod G, which is the orbit, the set of all orbits of the group action, this turns into a complex manifold whose dimension, as we expect it to be, is the difference of dimension of M and dimension of G. So, so this is one theorem. The another theorem simply follows as a corollary. We just take a Lie group, a complex Lie group, and a Lie subgroup, which is closed and normal, and then H will act on G by left translation or right translation, whichever we want it to be, and then the quotient group G mod H. H is normal, so this is a group first of all, and then by the first theorem, it also turns out to be a complex Lie group whose dimension is again the difference of their of the dimensions of G and H. Okay, so from these two theorems, we get that the complex torus is a complex manifold, and we also have these complex projective spaces. So for the complex projective space, by the analogy with the real projective space, so what we do is that we take Cn plus 1 minus the origin, and this C star is the group of non-zero complex numbers under multiplication. So lambda is a non-zero complex number, and z naught up to zn is an n plus 1 tuple belonging to Cn plus 1 minus the origin. So at least one of these zi's has to be non-zero. So then this is the group action simply by scalar multiplication. So then we can check that this group action is going to be holomorphic. It is free and proper, and that makes the space of orbits into a complex manifold. So this complex manifold is nothing but the set of all complex lines in Cn plus 1 passing through the origin. So and that set is called as CPN, or the complex projective n space. So CPN is then a complex manifold of complex dimension n, and as a smooth manifold, we know that CPN is nothing but it will be so this CPN will be S2n plus 1, which is the 2n plus 1 sphere quotiented with S1. So that's why it's a compact manifold as well. So CPN is a compact complex manifold of complex dimension n, and the coordinates of any point. So like this is an equivalence class of all the points which lie on the line passing through this point and the origin. So these are called as homogeneous coordinates. So this is the complex projective space, and then similarly we have the complex torus as well. So let us just take the complex plane C, like n is equal to 1. So the complex plane C, and then we take the uh, set of all Gaussian integers, z of square root of minus 1. So these are all complex numbers of the form a plus b times root minus 1, where a and b are only integers. So z of square root minus 1 is a discrete subgroup of C. So C is a group under addition. So this is a subgroup. It's a discrete additive subgroup. So it is normal. And then we can use this corollary to get that the quotient manifold, that the quotient is going to be a compact complex Lie group of dimension n. So its complex dimension is n, real dimension is 2n. So this is what we call as the complex torus. So that's why these the complex torus is a complex manifold, and then connected sums of complex manifolds are going to be complex manifolds, and that's why those uh, we have those compact Riemann surfaces of genera greater than or equal to 2 as well. Okay, and then another important example of complex manifold is a complex projective manifold. So this is nothing but we have this CPN. It's a submanifold of CPN given by the common zero set of some homogeneous polynomials in n plus 1 complex variables. So this f1 up to fk, these are some homogeneous polynomials in n plus 1 complex variables z0 up to zn. They can be homogeneous of different degrees. And then f1 up to fk, their common zero set. Uh, that is the intersection of all the zero sets of each, the intersection of the zero set of fj, j varying from 1 to k. So this is the common zero set of f1 up to fk. This the taken as a subset of CPN. So this will also be a complex. This in general is called as a projective variety because it can have some non-smooth points. But if it is a smooth manifold, means it does not have any singular points, then it indeed becomes a complex manifold called as a complex projective manifold. So the condition for this to be a complex manifold is that it just needs to be a smooth manifold. Then it will automatically turn out to be a complex manifold. So this is called as a so this is a submanifold of CPN called as a projective manifold. And then similar to the Whitney embedding theorem, which we have for smooth manifolds, which says that given any oriented connected oriented smooth given any connected smooth manifold, it need not be oriented. So given any connected smooth manifold of dimension n, it can be embedded inside some R2n or some r raised to the power some capital N for some large enough capital N. So uh, like it says that the Whitney embedding theorem says that any smooth manifold is up to diffeomorphism, a submanifold of some Euclidean space. So similarly, if, in complex geometry, we have this Kodaira embedding theorem, which says that given any compact complex manifold, connected compact complex manifold of dimension some small n, it will be a projective manifold, meaning it will have a biholomorphic embedding into some CP capital N for some large enough capital N. So that's why these projective manifolds are general enough that they are, for the most part, the only compact complex manifolds that we study. Okay. And then for I will talk about these almost complex structures. Up till now, we were talking about a complex structure on a smooth manifold, but we have a slightly weaker notion called as an almost complex structure. So here we first start with what is an almost complex structure on a vector space, on a real vector space, and then an almost complex structure on a smooth manifold is an almost complex structure on every tangent space of the manifold. Okay, so what is an almost complex structure on a real vector space? So take capital V to be any real vector space of dimension n. N is the dimension of the over the uh, field of real numbers. Then if we have such a linear operator J from V to V, which satisfies J square is equal to minus of the identity operator on V, then such a J is called as a almost complex structure or a linear complex structure on V. So uh, s- so this is a simple definition, and then the first observation that we make is that if a real vector space has an almost complex structure, then its dimension over the reals must be even. So why is that so? Because this condition J square is equal to minus of the identity operator. So suppose that lambda belonging to the reals is any eigenvalue of J, then it can be checked that lambda square will be equal to -1. Like we can just take a non-zero eigenvector, then j of v equal to lambda times v, apply j once more, then we will get that lambda square has to be equal to -1, and that cannot be possible. So which means that this j cannot have a real eigenvalue. But then if the dimension of the vector space were odd, then the characteristic polynomial is also of odd degree, so it must have at least one real root. But this j does not have any real eigenvalues, so which means that the dimension of v cannot be odd, so v has to be even dimensional. So if there exists an almost complex structure on a real vector space v, then its real dimension has to be even. So the thing is that this almost complex structure is like multiplication by square root of -1. So so that's why on this real vector space v, so now this almost complex structure will turn it into a complex vector space. So how is that? So now on capital V, we already have the additive abelian group, and we have scalar multiplication by real scalars, but we want to define multiplication by complex scalars. So let us try to define square root of -1 times v. So we have an obvious candidate that is equal to j of v. So then we can check that with this square root of -1 times v equal to j of v, this will make capital V into a complex vector space, and the dimension of this complex vector space over the field of complex numbers will be half of the real dimension, and that's why it will be n by 2. And then conversely, you take any even dimensional real vector space, it will always have an almost complex structure. Namely, we can, since it is having even dimension, n is equal to 2k. So we have a basis of the vector space, ordered basis of this form, v1 up to vk, comma w1 up to wk. So define an operator j from v to v by j sends every vi to wi, and j sends every wi to minus of vi. So and then extend j linearly on the whole of v, real linearly on the whole of v. This will make j's satisfy the property j square equal to -1. So on every even dimensional real vector space, there always exists an almost complex structure. And the thing is that given any even dimensional real vector space V with an almost complex structure J, we can always get a basis of this form V1 up to Vk, comma W1 up to Wk, such that J of Vi is equal to Wi and J of Wi is equal to minus of Vi. So this is how an almost complex structure on a vector space looks like. So now for the manifold, we just have to give an almost complex structure on every tangent space of the manifold, and this assignment should be smooth. So an almost complex structure on a smooth manifold is nothing but to every real tangent space, we assign an almost complex structure. So this J subscript P for every point P of the manifold capital M, J subscript P from TPM to TPM. TPM is the tangent space of the manifold at point P. So JP from TPM to TPM, that should be an almost complex structure on the real vector space TPM, and then this assignment to every point, this has to be smooth, meaning this j from tm to tm, which is the tm is the real tangent bundle, this should be a smooth vector bundle endomorphism. So this is called as an almost complex structure on a smooth manifold. So once again, if a smooth manifold capital M has got an almost complex structure, its dimension must be even, because every tangent space is having even dimension over the reals. Okay, and then this smooth manifold equipped with this almost complex structure is an almost complex manifold. So one thing which we can check over here as well is that every almost complex manifold is orientable. That one gets by taking a basis of this kind. That this basis will be an ordered basis giving an orientation to every tangent space, and then this orientation will become like so this assignment to every tangent space of this orientation will be smooth, which will make it a uh, orientable manifold. So every almost complex manifold is also orientable, and it also has got even real dimension. But the converse question, so over here
Yes.
every
Hello.
yes, sure.
I had a question here. I mean, you're introducing this almost complex structure. I mean,
Yes,
like given a vector space, we could also like by extension of scalars, like we can complexify the vector space, any real
correct,
vector
yeah.
space. So like has this like making the vector space through a complex vector space by introducing almost complex structure and by complexification, like are they totally two different things?
No, they are related. So okay, maybe I can uh, do that on the whiteboard. They are
And
related actually.
and one more thing, it would be nice like if you discuss a little bit like what is the tangent space like for complex manifolds. So how do we?
Okay, yeah, sure. I will discuss that. But first, I will answer your question about what's the
Yes,
relation
sure.
between the complexification of a real vector space and the existence of an almost complex structure on the vector space. So, okay, so now if we take a real vector space V, V is a real vector space, then V superscript C, which is the complexification of the real vector space, is uh, defined to be the take the vector space V, tensor product it with C, and this tensor product is over the reals. So what does this mean? So V is first of all already given to be an n-dimensional real vector space. C is a two-dimensional real vector space. So take the tensor product of these two vector spaces over the reals. So this is defined to be the complexification of V. And then the complexification of V, so this is nothing but we are extending the set of scalars from R to C. And so then if V was an n-dimensional real vector space, then this VC will be a two n-dimensional, if V was an n-dimensional real vector space, then VC will be an n-dimensional complex vector space, which will mean it will be a two n-dimensional real vector space. But on the contrary, if you have an almost complex structure J on V, then J makes this V itself into a complex vector space, whereas this over here we are having this VC, which is a different object. And but yes, still there is a relation. Namely, what you do is that in this complexification VC, this there is a square root of -1 eigenspace, and there is a minus square root of -1 eigenspace as well, with this operator j defined by multiplication by square root of -1. So then the square root of -1 eigenspace, that is what is called as the uh, for smooth manifolds, it is called as the holomorphic tangent space. And then this real tangent space can be identified with the holomorphic tangent space. So the idea is that this if this V has got an almost complex structure J, then V will be isomorphic as a real vector space to the square root of -1 eigenspace of its complexification. So that's the relation, that any real vector space having an almost complex structure, and then if you complexify it and take the square root of -1 eigenspace of the complexification, then V will be isomorphic to the square root of -1 eigenspace, and similarly it will be isomorphic to the minus square root -1 eigenspace as well. So yeah, so this is the relation. The only difference is that getting the complexification of a real vector space, we can do that for any real vector space, even for odd dimensional real vector spaces, but an almost complex structure exists only on an even dimensional real vector space. So yeah, so like that's the way in which they are related.
Okay, thank you.
Yeah. Okay. So now uh, the most important question is about the existence of these almost complex and complex structures. So on any even dimensional real vector space, we know that there always exists an almost complex structure. We can always define it in this way. But the question that then arises is on every even dimensional smooth manifold, does there always exist an almost complex structure? So it turns out that this is not true in general. And for the spheres a- Sn for all the even dimensional spheres, let us say S2n, where 2n is the dimension of the sphere over the reals. So for all of the even dimensional, out of all the even dimensional spheres, only S2 and S6, these are the only spheres which admit an almost complex structure, and the other even dimensional spheres don't admit an almost complex structure. So this is not true in general. So the thing over here is that on every tangent space, there will definitely exist an almost complex structure. So locally, we can surely get an almost complex structure, but when will these local almost complex structures patch up to give a global almost complex structure on the manifold? That is a topological question, and so that's why this is not true in general. Okay. And then of course we have the almost complex structure induced by the complex structure. So of course we should be expecting that every complex manifold should be an almost complex manifold. So there should be the almost complex structure induced by the complex structure.
Excuse me.
And yes.
Yes, so can you go to the last page? Like, I did not understand that part. Like, you are defining the almost complex structure. So on each tangent space, we are defining an almost complex structure.
Correct.
Then, like how are you gluing it up to like the full TM to TM? I mean,
Yeah, so that's what, like I said, that in general this gluing is not going to be happening. That's why I wrote that every even dimension smooth manifold need not admit an almost complex global almost complex structure. So that's why, like, so this is not true in general.
okay. Okay.
Like for vector spaces, it's trivial, you don't have to do anything, but for smooth manifolds, the gluing in general is not going to be happening. And as I said, for the spheres it happens only for S2 and S6. It does not happen for any other spheres. So all the other even dimensional spheres like S4, S8, S10, they don't admit any almost complex structure. Only S2 and S6 admit. So this is not true in general, that every even dimensional complex manifold admits an almost complex structure. This statement is not true.
Okay.
Okay, so now we have the almost complex structure induced by the complex structure. So uh, suppose that the smooth manifold already has a complex structure on it, then that complex structure will the holomorphic coordinates of that complex structure, they will naturally define multiplication by square root of -1 on every tangent space. So then just define j, j from the tangent bundle to the tangent bundle as j of any tangent vector is square root of -1 multiplied by the tangent vector. So every complex structure will be inducing an almost complex structure. And so if but it is not true that all almost complex structures come from some complex structure. So those which come from a complex structure, they are called as integrable almost complex structures. So an integrable almost complex structure is nothing but a complex structure, an almost complex structure which is induced by some complex structure. So we have criteria for the integrability of an almost complex structure. This is called as the Newlander-Nirenberg theorem. So this says that as I discussed in the beginning, the Dolbeau operators, which are del and del bar. Del is nothing but like del of f is nothing but del f by del z1 dz1, this and sum of this up to del f by del zn dZn. Similarly, del bar is del f by del z1 bar dz1 bar up to sum of this del f by del zn bar dzn bar. So these are the Dolbeau operators, del and del bar, and d is the exterior differential. So for any almost complex structure J on a smooth manifold, we always have these two Dolbeau operators, del and del bar, and because it's a smooth manifold, the exterior differential d will always be there. So an almost complex structure is integrable if and only if any one out of these three equivalent conditions holds true, that del bar square is 0, del square is 0, or d is equal to del plus del bar. So this is the Newlander-Nirenberg theorem. So we can explicitly check which almost complex structure is coming from a complex structure. So it then turns out that now first of all, the questions then in complex geometry are that given any even dimensional smooth manifold, does it always admit an almost complex structure? That itself is not true in general. And then suppose that it does admit an almost complex structure, then is this almost complex structure going to be integrable? Meaning, will it be coming from a complex structure? So that is also not true. Like this S6, which is the six dimensional sphere, that does admit an almost complex structure, but that one is not integrable. It does not come from a complex structure. And then the question of whether then S6 has some other complex structure, that is an open problem called as the Hopf problem. So like these are then some open problems in complex geometry regarding the existence of these things on a smooth manifold. Okay, so yeah, so this was about these complex manifolds. Okay, so like I think now I'm already out of time. Sachidanand, should I take some 5 minutes or like am I done?
No, you can take like that. That's fine.
Okay, so I can maybe take just some 5 to 7 minutes. So I will just introduce what are these Hermitian metrics and Kähler metrics. Okay, so like we know that yes, is anyone?
Yes. You said that if it is integrable, almost complex structure. I mean, what I understood that there could be infinitely many almost complex structure on a manifold. But if it is integrable, then integrable almost complex structure has to be unique. Like there is only one integrable complex structure one can expect on a manifold.
Yeah, is
Am
that
I?
true? That
So
uh,
basically, then there if almost complex structure is integrable, then there should be only one almost complex structure which is integrable. Is that true?
I don't. So, like, what you are trying to say is that if there exists a complex structure, so integrable almost complex structure means it's a complex structure. So, if on a
Yes.
smooth manifold, if there is a complex structure, then it has to be unique. Means there cannot be two or more complex structures on a smooth manifold. I
I-
think that is not true. So it is similar to your smooth structure. So is it true that on any topological manifold there is only one smooth structure? I think that is not true. And similarly, even for complex manifolds, I don't think it is true that
Okay.
the statement that like on the underlying smooth manifold, it can have only one at most one complex structure. I don't think that is true.
Okay.
But yeah, I'm not sure. I'm not quite sure about.
Okay. No, no. My question actually was that is it true or not?
I don't think so. Yeah, I don't think it is true.
Yeah. Thanks.
Okay. Yeah. So I will introduce these Hermitian and Kähler metrics. So on a smooth manifold, we have the notion of a Riemannian metric. So what does a Riemannian metric do on a smooth manifold? To every tangent space of the smooth manifold, it assigns an inner product, making that tangent space into an inner product space. And then this assignment uh, to every tangent space, it has to be smooth. So that is what is called as a Riemannian metric on a smooth manifold. Now, suppose we take a complex manifold and we take the induced almost complex structure. So the thing is that for dealing with the complex structure, we always deal with the induced almost complex structure. So okay, so now if we take a Riemannian metric on the complex manifold M, it will be interesting only when this Riemannian metric respects the additional structure on the smooth manifold, which is the complex structure. So when do we say that G respects the almost complex structure, or G is compatible with the almost complex structure? If so, on every tangent space TPM is the tangent space at point P, the real tangent space. Then on this TPM, this JP from TPM to TPM is a linear operator such that its square is minus of identity. So the Riemannian metric G is compatible with the almost complex structure J if this JP is an orthogonal linear transformation on every tangent space with respect to the inner product induced by the Riemannian metric. So this is what is called as compatibility of the Riemannian metric with the almost complex structure. And if a Riemannian metric is compatible with the almost complex structure, then it is called as a Hermitian metric. So okay, so this is what a Hermitian metric is. But now we want one more property for this Hermitian metric to satisfy, namely, given any Hermitian metric G, we take this real two form. So it's a 1, 1 form, means the holomorphic part is 1, anti-holomorphic part is also 1. We will see what these holomorphic and anti-holomorphic parts are in the next lecture. So the thing is that this is a real two form. So omega is defined in this way, that omega of x comma y is equal to g of jx comma y for all tangent vectors x and y. So this omega, we can check, it defines a smooth two form on the manifold. So then the metric G is to be a Kähler metric if this smooth two form is closed, meaning d omega is equal to 0. So this is a Kähler metric. And then the for every Kähler metric G, the associated smooth two form omega is called as the Kähler form. But because this G and omega will be in one-to-one correspondence, we say that we sometimes say in Kähler geometry that omega itself is a Kähler metric on M. So now over here, just to give some quick overview about what these Kähler metrics are. So basically, on a Kähler manifold, we have got three structures. So one is, of course, the complex structure on the smooth manifold. So to begin with, it's a smooth manifold. It has got a complex structure. Then it has got one more structure, which is the Riemannian structure that given by the Riemannian metric. And on top of it, there is another structure which is given by this smooth two form omega. So this form is called as a symplectic form. So so this is where symplectic geometry also comes into play. So this omega, so if on a smooth manifold capital M, if there exists such a smooth real form, two form omega differential two form omega, which is non-degenerate and which is closed, then this omega is called as a symplectic form, and then M with omega is called as symplectic manifold. So on this in this Kähler manifold condition, it is an underlying smooth manifold which has got three structures. One is the complex structure, one is the Riemannian structure, another is the symplectic structure. So the manifold is Kähler if and only if all of these three structures are compatible with each other. And all of these three structures are compatible if, first of all, the Riemannian structure has to be compatible with the complex structure, and that is same as saying that the Riemannian metric is a Hermitian metric. And then the symplectic structure has to be compatible with the Riemannian structure, which will mean that, which is same as saying that the symplectic form should be given by this expression, that omega of x comma y is equal to g of jx comma y for all tangent vectors x and y. So then, so a Kähler manifold is precisely a smooth manifold on which there is a complex structure, there is a Riemannian structure, and there is a symplectic structure, such that all these three structures are compatible with each other. So this is what is a Kähler manifold. Okay, so maybe I should stop now, and other things can be discussed in the next. Other prerequisites and preliminaries can be discussed in the next lecture. Okay.
Okay. Thanks. So, any questions from anyone? Okay. If not, then we will be meeting again on next Wednesday. I guess I'll tell what's the. I guess the
Sorry to
timing will be
interrupt. I
same.
had a question. Sorry to interrupt.
Yeah, sure.
Like I can't sort of make sense of the proof you gave for why almost every manifold with an almost complex structure is orientable.
Okay, so maybe I can write on the whiteboard.
You said to take this basis and sort of
Yes,
extend it by, and then by compatibility we'll get a oriented basis. So how do you do that?
yeah. So let us take capital M is a smooth manifold of. So first of all, if capital M is a smooth manifold, and if there exists an almost complex structure on capital M, then the dimension of capital M over the reals has to be even. So then if n is the real dimension of capital M, then n should be even. So n is equal to some 2 times k. Okay, and then so what we do is that we take so capital M is a smooth manifold. So take a local coordinate chart. It will look something like x1 comma some xk, and then uh, y1 up to yk. So this is a local coordinate chart on capital M. So what we do is that we take a local frame, which is del by del x1 at del by del x1, comma del by del xk, then del by del y1. So so it's a result that first of all, if on a real vector space capital V, if J from V to V is an almost complex structure, then we can always find the basis of that kind, of the kind V1 up to Vk, comma W1 up to Wk, such that J maps each Vi to Wi and J maps each Wi to minus of Vi. So similarly, one can check that on any smooth manifold capital M, if there exists an almost complex structure J, then around every point we can always find such a local coordinate chart x1 up to xk, comma y1 up to yk, such that this local frame, which is a so this is this set of locally defined vector fields, real vector fields on the manifold, del by del x1 up to del by del xk, comma del by del y1 up to del by del yk. These vector fields taken at a point P. So del by del x1 at some point P. Similarly, all of them at a point P. These will form a basis of the real tangent space TPM. So at a point P belonging to the manifold M, if we take the real tangent space TPM, then this del by del x1 at P, comma del by del xk at P, del by del y1 at P, comma del by del yk at P, this will form a basis of this tangent space TPM. So then, this basis will satisfy the additional property that this J, which is the almost complex structure. So J maps this del by del x1 at P to del by del y1 at P. Similarly, del by del xk at P to del by del yk at P. And then these del by del yi at P, they are mapped to minus of del by del xi at P. So J maps all of these vectors to these ones and these ones to minus of these ones. So one can always find such a local coordinate chart. This is called as the local coordinate chart, which is compatible with the almost complex structure, or which is induced by the almost complex structure. And then we take this ordered basis of the tangent space, and one can then check that this ordered basis gives an orientation on this tangent space, and then this will indeed give an orientation on the manifold, meaning it will indeed patch up to give an orientation on the whole manifold. Like I don't have the idea of the whole, like I don't know the details of the whole proof, but this is the idea that we have to consider this look this basis of the tangent space at every point.
So like to show compatibility, we'll have to look at the transition maps and take the
Yes, correct.
determinant there.
Yeah, so if there are two intersecting charts, some u1 up to uk, comma v1 up to vk is another intersecting chart, we'll have to compute the transition functions and then see how this basis transforms under that change of coordinates. And then we'll have to check that the two orientations, the orientation induced by this chart as well as by the chart u1 up to uk, comma v1 up to vk, the two orientations precisely match. So in that way, this will give an orientation on the whole manifold capital M.
Yeah.
Like that's the idea of the proof. Like even though I don't remember the details, but yeah, that's the idea.
All right. Thank you. Thank you.
Yeah, okay. Are there any other questions about these almost complex structures, or about these complex manifolds, or maybe Kähler metrics or Hermitian metrics on complex manifolds?
Okay. So we can thank Rajas, and we will be meeting on next Wednesday. Okay, then we can close the session for today, I guess. Thank you, Rajas.
Okay, thank you, Sachidanand.